So there are at least 6 things that clock software does. Let's look at them one by one. Maintaining the time of the day. Okay. So to keep the time of the day, operating system uses some memory location. Okay. And at that memory location, it counts at each clock tick. Clock tick means that remember this counter, when this counter reaches 0, it produces an interrupt. At each interrupt means a clock tick, okay? Each interrupt means a clock tick. So clock tick happens every maybe 60 times a second or maybe 50 times a second, at most 100 times a second. So when you keep the time of the day, okay, as an operating system, you have a special counter. If you keep counting each clock tick, okay, so you need some space. With a clock rate of 60 Hertz, that means that you have 60 interrupts happening every second. 32-bit counter will overflow in 2 years. Okay, so if you keep your time of the day and the date everything, so 32-bit counter will not be enough. It will be just over 2 years. So when the Unix operating system uses this 32-bit counter, it has some other it does some other things too. But for the Unix system, the time starts January. The time starts at January 1st, 1970. Okay. For the Windows system or the MS-DOS operating system, it starts January 1st, 1980. So these systems are keeping the time in terms of clock ticks after this date and this date. Okay. So the only thing to watch for is the number of bits in the time of the day count. So even if you use a 32-bit number, which is a very large number, it will not be enough for 2 years. So we have to do something else. Maybe you can use 64 bits. In this case, it will be much larger. Okay, it will be how many years it will take to fill in this 64 bits? For 32 bits, I have 2 years. Okay, for 32 bits, I have 2 years. So the rest of the 32, I will have 2 to the power 32 times 2 years. So it's a lot of time. This should be enough. This could be one solution, but we are not doing that. We are not going to use 64 bits because I have to update this number. 60 times a second. I don't want to deal with these kind of large memory locations. Biraz parlak mı? Şundan mı kaynaklanıyor? Okay, so the second solution is this one. Okay. They keep time of day in seconds instead of ticks. Okay, instead of ticks. Okay, tick means that every clock interrupt. Time of day in seconds means that it keeps the time of day in seconds. Okay. For 32 bits, so this is like 60 times 2 years, so 120 years. I have 120 years of time limit, which is very tolerable. I can do that. But to keep sub-second information for the current second, I keep another location. It is a number of ticks in the current second. So how many bits do I need for this one? Number of bits in the current second. This is keeping the second from 1970. How many seconds has passed from 1970? Okay, for the Unix system. And this is keeping how many ticks happened in the last second. So how many bits do I need here?
6 bits.
Nerede hesapladın?
60 defa alması gerekiyor. 64.
64 yeter gibi. 100 falan olsa da. Dolayısıyla buraya esasında 250 olacak hali yok. 8 bit, 7 bit fazla bile. 7 bits may be enough. 6, 7 bits. Okay. So I have the second information from here, and sub-second information comes from this one. And another one is another solution is this one. I keep my boot time in seconds. Okay, system boot time in seconds. I say that, okay, from 1970, I booted my computer. I booted my computer. I booted my computer, let's say yesterday, and this one keeps the number of seconds from 1970 to yesterday. So this is the number of seconds that passed that much time, okay? And this one keeps the number of ticks from my last boot time, okay? Number of ticks from my boot time. So how many? So this one is keeping the number of ticks for the boot time. So in 2 years, I will be out of bits in this counter, but no computer can be up for 2 years. You have to take it down, you have to reboot it, you have to maintain it. So this should be good enough for me. So I keep 2 counters. One is for the system boot time in seconds from 1970, and this one is the number of ticks from the boot time to the current time. So these are some solutions to keep your time of the day, including your year and the date information. Okay. So remember this Y2K problem, year 2000 problem. For most programs, especially for the personal computer world, they kept their date information using only the last 2 digits of the year, 1972. They ignored this part, they only kept this part. So when they reached 1999, okay, so they said that after 99 there will be 00. So 00 will be smaller than 99. That will create lots of problems for many softwares. So that was called the Y2K problem. So we have these kind of problems for our computers too. But I think for the Unix nowadays it is like somewhere, I think there is a problem around 2120. In more than 100 years, Unix systems will have serious problems. But we don't know what's going to. We don't know if Unix survives that many years. There is no reason that it shouldn't survive, because nobody knew that it would survive this many years. But still, we don't know. So these are some of the issues regarding to maintaining the time of the day. I cannot keep counting the interact ticks unless I have large enough buffer, or I use these kind of solutions. Okay, this was the first duty of the clock driver. Let's talk about number 2. Okay, preventing processes from running longer than allowed. Okay, so how do I do this? Whenever a process is started, the scheduler initializes a counter to the value of the process's quantum in clock ticks. Let's say a process started, process A, okay? I know that it cannot use more than 100 quantum, okay? 100 interrupt ticks, okay? At every clock interrupt, the clock driver decrements the quantum counter by 1, okay? When that number gets to 0, that means that that process used is quantum time, and it is time to switch to another process. So this is the clock drivers. By the clock driver's help, I can do this preemption operation. So I keep counting the clock ticks for each process. When I restart a new process, I put this quantum number in there. When I switch between the processes, I reset that number. Okay, so this is the task of the clock driver to decrement that number by 1. So it is doing this. So the clock driver is doing this for us. If I have multi-core CPUs, if I have many parallel CPUs, many processes can run at the same time. So my clock driver has to update the counter, decrement the counter of each quantum counter of each process at each clock tick. Okay. Another, remember, this was the third one. So the second one, third one is accounting the CPU usage. How much CPU did I use? Accounting the CPU usage. It is the task of the, again, clock driver 2. Okay. Other than counting the ticks for each process, I start a second timer. Whenever a process is started up, okay, a timer will be started. When that process is stopped, the timer can be read out and tell the CPU usage. So I know that that process used this much CPU time. Okay, so I keep adding that number so that I can do this accounting information for the CPU usage. If a process is using too much CPU, maybe I should inform the user. Maybe that process is using too much battery time on my mobile system. Okay. So some of these algorithms are expensive to keep. Some of them are cheaper, but they are not that precise. A simpler, less accurate version is this one. Okay. A pointer to the process table. I have a pointer to the process table entry for the current running process in a global variable. That global variable will keep my CPU usage time. Okay. And at every clock tick, I increment that value. By the clock tick amount. So instead of using a second timer, I do this automatically by the interrupt mechanism. I don't use any timers. Much cheaper. But the problem with this one is, at every clock tick, I increment that value by 1, but I cannot differentiate how much time is used by the process and how much time is used by the interrupt handler. So every clock tick is charged to the process running at the time of the tick. So the second solution is less accurate because even though it is cheaper to implement, it takes less CPU time. It is counting because it is counting the interrupt numbers for each process. It is not counting the CPU usage, real CPU usage. Even though it is easier to implement, it is less accurate. But we don't want to be very accurate for the CPU usage unless we are charging the users by the seconds. On my system, on this system, I don't have to be that careful. Maybe the solution is good enough. Okay, this is the third usage of the clock software. Again, maybe the most important one is this one. Maybe the second most important, one of the most important. Handling alarm system call from user processes. You know this C routine, when you say sleep 1000, that means that I want to sleep for 1000 milliseconds. Okay? When you call this function, okay, it makes a system call. Now your process is blocked for 1000 milliseconds. After 1000 milliseconds, an interrupt will be generated by the clock driver, and that interrupt will be handled and your process will be waken up. Okay, so this is called alarm system call. Okay, you are setting up an alarm. How does this work? Okay, a process can request the operating system give me a warning after this time passes, and we talked about the cases where we might need it. Okay, so the clock driver might keep a table inside the table. Okay, inside the table, let's say like this one. Process A, B, C on and maybe another process A again, etc. And this is the time to wake up, okay? And this is my current time. Let's say my current time is 4:21. Okay, this is the number of ticks from the boot up time. This is my current time, and process A wants to be waken up at this one. Maybe this one is 42,500. This one is 42,550. And process A wants to be waken up again here. Okay, it has a table. It has the process names and the time where you need to send the signal to the process. Okay, so one way is to maintain such a table in which the signal time for all the pending timers is kept, as well as variable giving the time of the next one. So the time of the next one will be a little bit different. I will show you the picture. Whenever the time of the day is updated, okay, the driver checks to see if the closest signals are occurred. When you update this one, when you update this 4201020101, you compare it against these numbers, okay? You compare it against these numbers. If it is same with one of these numbers, then you wake up the process. If it has, the table is searched for the next one to occur. So this one requires a linear search of the numbers. This is not good. So instead of doing this table, we have such a structure. Current time is this, okay? And I have a linked list of processes. I have 1, 2, 3, 4, 5 signals pending. One process says that, let's say this is process A, B, C, D, and A again. Process A says that wake me up at this time. The time is currently this one, okay? The time is currently this one. Instead of keeping this table, using these absolute numbers, it is keeping it this way, okay? Says that process A needs to be waken up in 3 interrupt ticks, okay? In 3 interrupt ticks, because it needs to be waken up at 4203, okay? 4203. So this is the current time. I put number 3 here. And this one is after you wake up this one, in 4 interrupt cycles, you will wake up this one, and in 6 interrupt cycles, remember, the difference between these two is 6, okay? In 6 interrupt cycles, you will wake up this one, and in 2 interrupt cycles, between this and this one, okay, it's 2, you will wake up this one, and finally you will wake up this one. So this is our structure. I don't need to make any searches. I know that when I increment, okay, when I increment this number by 1, okay, next signal is decremented by 1, okay, and I incremented this again. This became 2, and this became 1, and this became 3, and this became 0. In this case, I will just remove this one, and I will wake up the process number A, process named A. So after this, my time is 4203, and my next signal will be 4, because now this one is at the beginning. I don't need any checking, okay? This is 4 by the way. 4, okay? I don't need to update the table entries. I don't need to make any changes. All I do is increment the current time, decrement the next signal. When this one reaches 0, take the first one out and continue this way. Okay? So these numbers are not changing at all. So this is one algorithm to handle the alarm system calls. You don't expect that there is only one alarm signal code. There might be several, because we are running a multi-process operating system. Okay, there might be several, and each of these might submit several alarm system calls. So we need to be careful about this. This one might be very long. It doesn't matter. It doesn't cause many problems. When you receive a new signal, let's say sleep, okay, sleep 100. So what do I need to do is I need to find a place in this linked list, okay, for 3 plus 4 plus 6 plus 2 plus 1. So that means that 13, 15, 16. At the end, I will put what number here? You tell me. So this is 16. I get this sleep 100. So I will put
86.
yes 84. Okay. After you wake up this one in 84 interrupt cycles. This interrupt cycles, let's assume. In 84 interrupt cycles, you will wake up my new process. Okay. So only time you need to make a search in this linked list when you receive this new system call, and which will not be that frequent. So you don't have to worry about the complexity of this table maintenance thing. Okay. Any questions?
Hocam mesela burada 4200 yerine 4216 yeni bir proses sleep dediğinde daha önce koyabilir mi yani?
Tabii koyabilir. Yani sleep 10 de sleep 10 nereye koyalım söyle. 3, 4, 7. Şu araya 1'e koymam lazım. 7'den sonra şuraya bir tane 3 sıkıştırmam lazım. 3, bu da böyle. Ama bunu koyduktan sonra da şimdi bunun arasında şey vardı ya,
evet.
6 gidecekti. Bunların her birini teker teker 3'er düşürmem, buradan her birini 3'er tane düşürmem lazım. Bu 3 olacak. Yanlış mı söylüyorum?
Hocam.
Tamam yok, sadece bunu düşürdüm. Güzel. Sadece bir tanesini düşürdüm. 3 olacak. Gerisi aynısı. Evet.
Hocam pending time'ları aynı olursa ne oluyor? İki proses.
Arkaya koyuyorsun onları.
Peki mesela bir tanesi yaptığı zaman...
Şu 3, bu da 3 olacak. Değil mi? Pardon, 3 olacak, bu da 0 olacak burası. 3'ten sonra 0 bekleyeceksin. Dolayısıyla o adam en baştakini aldığı zaman arkasında 0 var mı diye, ya da zaten bu 0 alıp buraya koyacak ya, bu da gelmiş diyecek, hemen onu da yapacak. Yani update etmesi çok zor değil, ortaya bir şey koyması zor bir şey değil. Tamam. Var mı başka soru? So this is one of the most important tasks of a clock driver, which is handling the alarm system calls. Okay, we talked about already watchdog timers. Let's see it again. I think okay. Embedded devices to detect problems such as hangs. If there's a hang, then my watchdog timer will cause an interrupt. Normally I don't expect any watchdog interrupt, but if there is a watchdog interrupt happening, that means that somebody didn't reset that watchdog interrupt properly. So there is a problem. I should solve this problem. Okay. So I already talked about this. I'm not going to repeat whatever I repeated unless you have any questions. I will move on. Okay. Again, for keeping statistics, monitoring, profiling, for some users, or maybe for debugging purposes, operating systems use these clocks to build up a histogram of information. When you say that I want to watch this process, give me information about how much CPU it is using, what kind of memory location it is using, where it is spending its most of the time. Again, I use clock software. I get the help of the clock software, clock driver, to keep that information. We already talked about this. So clock is an I/O device, specialized I/O device, but again, it's an I/O device. It has a driver, and it has a controller. It has a device itself, as I showed you here. Okay, like this one has a controller and a drive itself. This one has a clock device and the device controller and the clock driver. You need to write the driver, and the driver is part of the operating system. But it is a little bit different from the other I/O devices. How it is different? It is not a character device, or it is not a clock device. You don't do lots of information input and output with the clock I/O device. Okay. All you do is you give a number to the clock driver. Okay, wake me up at this time. Okay, it produces an interrupt. Okay, or you ask the clock driver to give you the current time of the etc. So there is some kind of limited input output, but it is not like the reading from the disk or reading from the network drive. Important device, important driver, but a little bit different from the others. Okay. Any questions about the clocks? So at the end of this chapter, we have keyboards, mouse, and graphical user interfaces. I will talk a little bit about more of them. Okay. Then I will spend tomorrow and the next day talking about deadlocks. Okay. Deadlocks are important in that there is lots of literature on deadlocks. Okay, lots of techniques in deadlocks. So the deadlock chapters are very, very large in the operating system books. But the thing is that no operating system, no current practical operating system uses any deadlock mechanisms. Okay, they just ignore the deadlock problem. So I don't want to spend that much time, even though the literature talks about the deadlocks a lot. I am going to talk about deadlocks just because the book has it, and everybody is talking about them. But deadlocks are just ignored by the Windows, by the Linux, by the Android, by the iOS. Nobody is using any deadlock-related stuff. So why should I spend time on them? But again, maybe if somebody asks you what's a deadlock, you should know about it. So let me go back a little bit. I think I missed this part. Soft timers. Okay. This is a very important concept. Soft timers. Okay. So when we do remember doing the I/O, we said that we can do the I/O either by programmed I/O. Okay. You wait, you do polling. If the I/O device is ready, you do your I/O. Or you do it by interrupts, or you do it by the DMA, right? Three things. Okay. Let's compare interrupts and polling. Okay. Interrupts have very low latency because if the data is ready, the I/O device causes an interrupt, and an interrupt is handled by the CPU. Okay. So this was a very good solution in the 1970s, 80s. Okay. Because when the interrupt happens, all you need to do is you save your program counter, you save your program status word, stack pointer, and that's it. If you consider your CPU 8080, okay, from 1974, that was it. So the interrupts were very, very fast, agile, and very, very cheap. Nowadays, it is not the case. When you have an interrupt, okay, since we have very complicated cache mechanisms, okay, megabytes of data, very complicated pipelining architectures, okay, usually the single CPU executes four or five instructions at the same time. Sometimes I am super scholar, so the picture is more complicated. TLB, my paging stuff, okay, my virtual memory. Remember that my page tables are very, very large, and when I switch between one process to another process, I need to invalidate all of my TLB stuff, my caches, and all that kind of stuff. So the interrupts are becoming so expensive. If you receive 60 times interrupt, okay, in a second, you are running into maybe 10, 15, 20% CPU inefficiencies, wasting of your CPU time. So we should avoid interrupts. What is the alternative to interrupt? Is polling. Polling is something very, very inefficient. They are much more inefficient than interrupts, because you have to wait until the I/O device is ready. You're wasting your CPU time. So instead of using interrupts and polling, somebody has suggested that let's use soft timers, okay, to avoid interrupts. Okay. In the soft timers, you don't produce an interrupt when the timer is ready to produce an interrupt. Instead, okay, whenever the kernel is running for some other reason, When do I run the kernel? When I make a system call, right? When there is a cache miss, when there is a page table mess, etc. You have to run the kernel in that case. Whenever the kernel is running for some other reason, just before you come back to the user space, okay, it checks the real time clock to see if the soft timer is expired. So you don't produce, remember, when I reach this number to 0, okay, I say that, okay, I need to produce an interrupt here, because I need to produce an interrupt here because somebody needs that interrupt. Instead of doing this, instead of producing an interrupt, I do this checking, okay, I do this checking whenever I am running my kernel, okay, because I have to run the kernel mode many times a second anyway. At the end of I did my kernel service, I check if a real-time clock, if a soft timer has expired. If there is a timer is coming up, okay, I say that, okay, this process needs to be waken up. This process needs to be warned that this timer has expired. So I don't use any interrupts here for the timers, okay. So this is saving lots of CPU time because I am not using the interrupts. And since I am in the kernel mode anyway, I got that hit to go to the kernel mode. I already paid that price. When I pay that price, I am doing something else at the same time. So I am not paying the same price for the hard timers. Okay, that's the idea of the soft timers. Okay, so I should be in the kernel mode frequently. For the kernel mode to be in kernel mode, I need system calls, which happens a lot. Translation look aside buffer misses. Again, something to do with the virtual memory, page faults, I/O interrupts, CPU going idle. So all of these stuff already cause kernel traps. When I'm in the kernel trap, when I am done with the kernel, before I go into the user mode, I check this table. Remember this table? I check this table. If any process is, if any of the timer is expired, if any of them is expired, then I wake up whoever set up that timer. Okay. So that means that I might be a little bit late. Because that time is precise. When the interrupt happens, you immediately send an interrupt. It immediately sends an interrupt to your CPU. This time you have to wait until a kernel call, kernel switch occurs. Okay. So sometimes a 10 microsecond latency might happen, but for most of the systems, for most of them, this is okay because instead of eating up 35% of the CPU to handle these kind of timer CPU calls, okay, timer CPU interrupts, I will be much more efficient. The trade-off will be I will be a little bit late for some of the timers. So that's the idea of soft timers. Don't use the interrupts for everything. Okay. If your job is not time critical, if a little bit latency is okay, then use the soft timers. When you are in the kernel mode already, check to see if any of the timers are expired. Okay. So this is the last thing that I will talk about the timers. Much more efficient of implementation of the timers. Any questions? Maybe one of the most frequently used I/O devices, keyboard. Okay. Keyboard uses typical interrupt mechanism. Okay. Most of the keyboards, all of them actually, they have embedded microprocessors, and using that microprocessor, you communicate with your computer on a controller chip. Okay. When you press a key, your I/O device, keyboard I/O device, produces an interrupt. Okay. When you release the key, it produces another interrupt. So when you press one interrupt, when you release another interrupt, each key press means that there are two interrupts for each key press. Okay. At each of these keyboard interrupts, the driver extracts the information from the keyboard and sends that information to the computer, and everything else happens in the software and is pretty much independent of the hardware. So it's a very simple interface. Usually the information comes from the keyboard to the computer side. For complicated, more enhanced or advanced keyboards, information might flow from the computer side to the keyboard to modify some stuff. Okay, so for the keyboard software, there is not much to talk about actually. Most of the keyboards have 128 keys, so only 7 bits are needed to represent the key number. You don't send the ASCII code because the keyboard doesn't work with the ASCII numbers. Okay, you send the key number when you press a button. Okay, you send the key number, and that key number will be one of these 128 keys. Okay, at the upper levels of the keyboard handling, there are two modes of the keyboard usage. One is the raw mode, the other one is the cook mode. Okay, in the raw mode, okay, whenever you press a button, your application knows it. Okay, whenever you press a button on the keyboard, a key, your application knows it. In the cook mode, no, you provide all the whole line, 8 characters. When you press the enter, your application gets it. Okay. Remember how the scanf works? Okay. How does the scanf work? When you say scanf something, it gives you the whole line. It doesn't give the characters one by one. Okay. You write the whole line. You do your editing, backspace, etc. That kind of stuff. When you hit the enter button, your scanf receives the whole line from the operating system. It's called the cook mode. Okay. For scanf, it works this way, but sometimes I want to know if a keyboard is pressed. In that case, you will use the raw mode. Raw mode is more expensive than the cook mode because at each key press, there is a communication between your software and the operating system, which requires some kernel mode switch, which is expensive. Cook mode is less expensive, more efficient, but it is less flexible because you need to wait for the user to write the whole thing. You cannot do any interventions when the user is writing something to the screen. Okay, I will skip these. Related to the keyboard, we have the mouse. Okay, we used to have mechanical mice. Okay, we used to have mechanical mice. Nowadays, our mice is optical. Okay, so keyboard is very simple. When you press a button, it creates an interrupt, and in the interrupt handling routine, you send your key number to the interrupt handler. Okay, that's how the keyboard interrupts work. How about the mouse? When you move your mouse, or when you click one of these buttons, again, an interrupt is created, and with this interrupt, you send this information: delta X, delta Y, and the button configuration. What is delta X and delta Y? Delta X and delta Y are the distances that your mouse has traveled from the last position that you generated your interrupt. Okay, so let's say in my screen, okay, my mouse was here. Okay, I moved my mouse from this position to this position, and that caused some interrupt, so I will send this part as delta X and this part as delta Y. If I click one of the buttons, left button, right button, or the scroll button, and there will be some button information. So That message from mouse to the computer will include this information. Okay, so it is information that you are sending is only relative. Okay, you are not sending the absolute X, Y information. You are sending only the relative delta X, delta Y button information. Okay, so usually 40 times a second at most. So you are creating 40 times 40 interrupts a second when you are doing this mouse hand. Okay, so this is the second most used I/O device regarding the computers. Let's talk a little bit about user interfaces. This is the mother of all the user interfaces, X Windows system. Okay, and this was based on this was developed at MIT. Okay, but this was X Windows did not invent the graphical user interfaces. Before that, in 1960s, somebody already was using the mouses and the keyboard clicks and the menus and the windows, etc. in 1960s. So again, that guy was at MIT too. They developed on top of that system. They developed the system, and in fact, again, this system is coming again from Multics. Multics. What was the main idea of the Multics? Multics said that, like, as I am receiving my electricity from the network, my water from the network, why shouldn't I receive my computing needs from the network? Okay, so that was the idea in the Multics. Multics said that, okay, I am running the processes on my centralized computer, and I will send the outputs to the users' computers at home. So they developed this method. This is my server, this is my remote host, okay, and this is my computer at home, and this is my network. My applications are running at my remote host, okay, my window manager application programs, okay, and my X library is this stack, okay, this is running in the user space. X Windows system, okay, X Windows system runs in the user space, that's why it is very portable. It is not part of the operating system, okay? It is part of the user space. It runs in the user space. It doesn't crash your kernel at all because it's a user process. At most it crashes your GUI, okay, that's it, but operating system is running underneath without any problem. Since it is running in the user space, it is very portable. That means that it is not part of the operating system. It is not dependent on any of the hardware. It is not dependent on any of the operating system details. It uses the POSIX system calls to make its calls. So that's why it is very portable. If I have a X Windows system running on Unix, then I can port it to Linux, or maybe I can port it to OS 10 of the Apple, because the interface is almost the same. Okay, so originally it was invented for connecting a large number of remote users. Okay, but later they said that maybe I can run the remote host and my local system at the same computer. So these two merge together most of the time. So this is my X Windows system. At the lower level, I have my X client, X library, intrinsics, and motif. GUI happens here. Okay, buttons, windows, and these are the very low level X window primitives. This is like an operating system, but it runs on top of the operating system. At the client, at the server side, okay, I have only a single layer of software. So at home, my task is very, very easy. Okay, I just show the results. All the calculations, all the application related stuff happens in a remote host, which is more capable, which is more advanced. That was the idea. Again, later they moved all of the stack to this part, and nowadays I am running my X window libraries, interests and motif on the same computer. Okay, so maybe a few examples. Okay, this is a skeleton of an X window application program. Of course, it is written in C. Okay, these are my C. This is graphics context. You know, you remember from your Java programming classes. Okay, you open an X window display, and you open your sample window, and there is a infinite loop here while running. You get your X window system is event-based system. You know what event-based system is from your Java classes again. X window is an event-based system, but even event dispatching loop is handled by you. You get your event, you do your switch, okay? You do your switch. If it's a button press, you do this. If it's a key press, you do this. Nowadays we are not doing this, okay? Nowadays we are using polymorphism. We say that, okay, this loop is run somewhere. It was run generically long time ago. What I do is I provide polymorphic functions to these functions. So what I say that if there is a key press, then that key press will be handled by this function. I provide the functions only. Nowadays my task is much more easier than this. This was straightforward C application without any object-oriented structure. That's why these two slides, it is hiding lots of details. Usually writing a simple, showing a simple window on the screen takes more than 100 lines of code, which will take only a few lines of code for the simple Java application. So this is one example of a X window system. And the rest of the GUIs are kind of motivated from the system. And Microsoft Windows or the other types of graphical user interfaces have their roots in this X window system. Okay, I will not much talk about. Again, this is an example for the Windows GUI. Very similar, get message and do the super loop, okay, and handle message. There are callbacks. Instead of doing this switch, it is doing this callbacks. It's very similar to what X window was doing previously. Okay, that's it for the I/O chapter. Tomorrow I will start talking about deadlocks. If there are no questions, I will stop here. Bir tane soruyla ilgilenin. Okay.
Do we have separate APIs for soft timers and
Do we have what?
a separate API, OS API?
Yes, that's true. When you say that if you want a hard timer or soft timer, you indicate that. Yes. Otherwise, I mean, sometimes it is critical that you receive your interrupt at the exact time. You cannot wait. If you wait, you will lose that data maybe. Otherwise, it's very fast. Okay.
This will, I mean, like the soft timer mechanism did not do any interrupts to the CPU. So now the interrupt will happen, and
Yeah.
the switching will happen anyway.
But I mean, there's a trade-off between should I be more efficient or should I be more precise? For some applications, it doesn't matter if it is if you are precise or not. But for the others, it's okay. I can be 10 microseconds late. I mean, it's a decision of the application program. And while that hard interrupt occurs, hard timer occurs, since you are in the kernel mode, your soft interrupts will be handled at the same time. Okay. So that's it for today. Tomorrow we will continue.
Geleceğe yatırım ya. Servet
Neyler arası?